Okay. Hey everyone, we are looking at Mastery Question 10, Problem 1C. And it says, how many grams of CO2 are produced when 1.424 moles of CO2 are produced? We're looking at random numbers. Your numbers probably aren't the same. So what we have to do is figure out how much CO2 is produced. Now this is different than the other problems. So this is still the same chemical reaction, which is this C6H10O6 reacting with O2. Oh no, just decomposing. Just decomposing to C2H6O plus CO2. And Emmy, did you balance this chemical equation?
Yeah, I balanced it.
Okay. I'm going to go ahead and try to balance it, and we'll see how much I mess it up in the process. Good place to start is carbons, hydrogens. Okay, so trying to figure out the best place to start. Best place to start is going to be the hydrogens because there's only one hydrogen and one hydrogen. The carbons and the oxygens are all over the place. So I'm going to start with balancing the hydrogen. And 10 and 6 is going to be a common factor of 30. So I'm going to go with 5 and 3. So that's 30 hydrogens and 30 hydrogens. Am I even close to the right answer yet? Look, don't tell me. We'll see how I go. This gives me 18 carbons. And, right, 3 times 6, math in my head is hard. 18, okay. And here we've got 5. This is 18 carbons, 18 oxygens. So I've got 5 oxygens, and if I want to get to 18, oh, that's not going to work, is it? Let's keep going.
Just an FYI, on mine it says C6H12.
Oh, that's going to make my life so much easier, thank you. I had a typo, thank you. Oh, I was getting really worried. So first thing about balancing chemical equations, if you don't have the right compounds, it gets bad real quick. So that means in order to get to 12, I just need a 2 there, common factor. Whew, okay. Now, hopefully this will make a little bit more sense. That's 4 carbons. I don't need a weird coefficient out here, so my hydrogens are good. That's 4 carbons. If I had a 2 here, that would be 4. That would be 4 carbons plus 2 carbons is 6. And then I've got 2 oxygens plus 4 oxygens. That's 6. It's balanced. Okay. That was much easier to balance than the thing I was trying to do, thank goodness. Now, in terms of how we interpret this, the previous problems had some amount of reactant, and you figured out how much product was made. And the thing that's kind of, and also, Emmy, is this the balancing you got?
Yeah, that's what I got.
Okay, good. Much better than the thing I was trying to balance. So when we start thinking about this, I think about chemical reactions almost kind of as recipes. And what this is telling us is, if I have this amount of ingredients, I can make these things. And everything's kind of related to each other, so I can think about this in 3 different relationships. I can say that 1 part, and I'm going to use moles because we're in chemistry, right? 1 part of C6H12O6 used will result in 2 parts, or 2 moles, of C2H6O produced. We usually use off the used and produced because the chemical reaction is already telling us this. So that's one of the ratios we can look at. We can also look at the fact that 1 mole of C6H12O6 is related to 2 moles CO2. Or we can look at the reactants related to each other. 2 moles, and I'm going to pick this in a particular order. Oh, I'm looking at the wrong one. That's why the numbers look weird. 2 moles of CO2 for 2 moles C2H6O. So this gives us a way where now I could take any one of, if I had any one of these things, I could relate it to the other things in the reaction. So for this particular question, so this is the one, let's see. For part A, we use the second one, because that's asking about CO2 produced from the C6H12. For part B, we're also using this one because it's asking about the moles of CO2 produced. And for part C, from the same product, it's just instead of being moles, it's grams. And for part C, it's asking for CO2 produced relative to the amount of C2H6O produced. And the chemical reaction tells us that for every mole of for every 2 moles of C2H6O produced, I also need 2 moles of CO2 produced. So if we've got 1.42, I can use this relationship on the bottom to essentially, the relationship from our chemical reaction, our recipe, tells us that the amount of C2H6O produced is going to be related to the amount of CO2 produced. Mathematically, it's really boring. Right? Because it's a 2-to-2 ratio, or if you'd like, a 1-to-1 ratio, the moles of CO2 produced are equal to the moles of C2H6O produced in this situation. Then, in order to get the mass, all we have to do is take that number, 1.42, multiply by the molecular weight, and that should get us the right answer. Based on the number that you got, Emmy, my guess is you had a mistake in your mole ratio.
Yeah, I think I was just overcomplicating it with all of the dimensional analysis. But so all that we have to do is multiply 1.42 by the molecular weight of CO2?
Yeah.
Or...
Yeah.
Okay.
So, and notice that this is one of the traps of stoichiometry. Is one, it's easy to overcomplicate it, and two, from an instructor standpoint, it's easy to oversimplify it. Because I could have said, oh, just take 1.42 and multiply by 44. But the reasoning and the logic behind why that works is really the important part of this. Why does multiplying that number by 44 give us the moles of CO2? It's because the moles of C2H6O are going to be equal to the moles of CO2 based on our chemical equation. And because that's true, multiplying by 2 divided by 2 is mathematically really boring. It's just multiply by 1, which is do nothing. But the unit analysis of how the units change is kind of the important part for stoichiometry.
Okay, thank you.
You bet. Okay, the next problem we're working on is Mastery Question Set 12, number 3. And I'm going to read this out. It sounds a little confusing, and then we'll draw some parallels into how it's the same from other things we've done. A researcher creates a new manganese sulfide semiconductor, but doesn't know the oxidation state of manganese. She can get the oxidation state from the stoichiometry of the compound, but that's also unknown. So we go through and we do some reaction analysis. Reacts the semiconductor with magnesium sulfide with nitric acid, which oxidizes the sulfur into sulfate and the manganese into permanganate. Take the result and dilute it into 250 mils, And then you can use inductively coupled plasma to figure out the concentration of each acid in the solution. Inductively coupled plasma is a really cool spectroscopic method. It relates to the stuff we did earlier in the quarter. You get the concentrations of permanganate and sulfur in the sample, and then you ask, what's the empirical formula? On its surface, even when I read that, I was like, what is it talking about? But let's just start with the things that we know for sure. We know that we're starting with some manganese where we don't know how much manganese, and some sulfide where we don't know the sulfur. Right? So that's a great place to start. We also know we're doing some reaction with nitric acid. And that reaction with nitric acid is going to produce permanganate and sulfate. And probably some other things because there's got to be nitrogen someplace. But these are the two things that we care about because we can see this connection that this amount of manganese is going to be that amount, right? There's a direct correlation there. This amount of sulfur is going to be that amount. And we actually, because the products are also 1-to-1 ratios, are just one manganese, one sulfur, we actually don't even need to balance this and figure out the stoichiometry because that inductively coupled plasma thing is going to tell us the moles of this and the moles of this. So we don't even need the stoichiometry to do this. This is just to kind of exemplify why we can use just these two results to get this material. So let's go ahead and think about the two things we know. We know that the concentration of manganese, and again, my numbers might not be the same as yours, so make sure you're using your numbers. The permanganate has a concentration for me of 0.01164 micromolarity. And we also know that it was in a solution that was 250 milliliters. Let's call this 250 milliliters. Right? Concentration times volume is going to give us moles of permanganate. And then just like the analysis we were doing with combustion analysis, I can take my moles of permanganate and I can figure out how many moles of manganese must be in that because I know that there's 4 oxygens and 1 manganese for every mole of permanganate. Let's do that calculation just for the permanganate, and then I'll let you do the other half for the sulfur. First thing, careful with the units. I'm going to go ahead and rewrite this, taking into account the units. MnO42 minus times 0.0116 times 10 to the minus 6 moles per liter times 0.25 liters. Notice with this type of writing, sorry, not manganese times that, this is just manganese. With this way, the liters will cancel out and I'll just be in units of moles. So I'll go ahead and do 0.0116 times 10 to the minus 6 times 0.25. And whoa, scientific notation. 2.9 times 10 to the minus 9 moles MnO42 minus. Really small number of moles. This must have been a really tiny starting sample. Notice it doesn't give us the, oh, it does give us the original mass of the starting sample. Great. I wonder if we'll use that. Let's find out. To get from just permanganate to just the manganese, I'm going to go 1 mole of manganese for every 1 mole MnO42 minus, right? Because there's only 1 manganese in there, this multiplication is kind of boring. That's 2.9 times 10 to the minus 9 moles MnO42 minus gives us 2.9 times 10 to the minus 9 moles. And then right? And so that is the moles of manganese in that sample. The next thing we have to figure out is the moles of sulfur. Making sure I didn't forget anything as I'm looking at this. So just for those of you that are in office hours right now, does this process kind of look familiar and kind of make sense compared to our combustion analysis? And you can use participants and put yes, no, or you can unmute yourselves.
Yeah, it makes sense.
Cool, yeah. So this is, instead of burning with oxygen, we're digesting with acid, but the same kind of thought process is still there, right? So this is going to be our moles of manganese. We're going to do the same thing with our moles of sulfur, and then we're going to have that XY ratio of manganese to sulfur. And then we can divide by the smaller number and get the correct ratio. And that's going to allow us to figure out what the composition of our new semiconductor, our manganese sulfide semiconductor is, and then we can go look it up and get the correct chemical name, or we can just name it properly with manganese something sulfide. Okay. I want to finish this problem, but should I finish the problem?
Yeah, you should finish it.
Okay. I had a feeling I should finish it. But I'd like everyone to have to work on it some. So let's go ahead and do this. 2.9 times 10 to the minus 9 moles. That's for that part. Now I'm going to erase this, and I'm going to do the same thing for the sulfur. Same volume. I'm going to switch colors so people can tell I'm doing something different. Let's see here. So my sulfur concentration, my sulfate concentration was 0.02911 times 10 to the minus 6 moles per liter times 0.25 liters. And I'm even going to put in an extra step here, times 1 mole S2 minus for every 1 mole SO4 2 minus. So I'm essentially taking into account the mole ratio. So instead of doing it in 2 steps, I'm doing it in just 3 multiplications right away. Mathematically, I feel okay with that because you're just multiplying by 1. Chemically, it's really important that we realize that's happening, though. And we get 7.278 times 10 to the minus 9 moles of sulfur in that sample.
I'm a little bit confused. Since they both had the same concentration, where's the difference in...
No, they didn't have the same concentration. The permanganate concentration was lower than the sulfate concentration.
Oh, okay. In mine, for some reason, they have the same concentration.
You have a different unknown. It's possible. So your scientist, your researcher made a different manganese sulfide than my researcher. So you've just got a different ratio. But the process should still be the same.
Yeah.
So this sulfur is going to be 7.278 times 10 to the minus 9. 2.9 is the smaller of those. So I'm going to go ahead and divide. And I'm also going to, you notice the times 10 to the minus 9 is the same, so I'm just going to call this 2.9 nanomoles. And this is going to be S, which is 7 point, I feel like I should have more digits than 2.9, and 7.28 nanomoles. I'm going to divide by 2.9 for both. That's going to result in, well, I can do the first part by myself, Mn1, sulfur, 7.28 divided by 2.9, 2.5. And this is where a lot of people make mistakes. We addressed one of these earlier in office hours. Sorry, I wasn't recording it. But in this situation, this is where people get really trigger happy with rounding. You know, you see 2.5 and you're like, oh, that's 3. We have to be really careful in this because this is actually the correct ratio. So we don't want to, if we just round this to 3, then it wouldn't work with all of the rest of the math we did. So instead of rounding this to 3, we're going to find the smallest whole number ratio without doing any rounding. And the things I think about is 0.25 is 1/4, 0.33 is 1/3, and 0.5 is 1/2. So I'm going to be looking for things like 0.25, 0.33, and 0.5, or 0.75 or 0.66, you know, those things that I can relate to fractions. So this is like 2.5. Obviously, if I double it, I'm going to get Mn2S5. And this is going to be our empirical formula. So from the empirical formula, we can figure out the oxidation state on manganese, assuming that sulfur is a -2. And then we can look up this manganese, or we can name the compound as well. Did yours work out, Emmy?
I'm still working on it.
Okay. No worries.